Hey guys! So, congratulations on finishing that last exam. I got some good news, and I got some bad news. So, the good news is, you've actually covered the majority of everything that's really important in this class. We're really not going to be learning all that much new from this point on. We're just going to be learning how to apply what you've already learned. The bad news, I told you I'd never lie to you. I'm going to be totally honest. This lecture is probably the longest and hardest of the material we have to cover all semester. It's not really any harder than anything you've ever covered before, but it's going to take a long time to solve these problems. The good news is like I said, we're going to do it now, get it over the way. I actually pulled it forward just to get it over the way. And the second thing is, I want you to pay really close attention to this lecture. I've been teaching this for a long time, and I think I found an easier way to do these problems than the book does them. So look at this circuit. What's new? This circuit is unlike any circuit we've ever solved before because of one reason. Can you see it? I can feel it through the screen. I think you see it. Do you see it? What's this? Oh my god! We have two voltage sources. That's it. I quit. I'm going home. Can't do it. But we can. We actually can because circuits are linear. So I'm going to show you how to solve these problems. It's no harder than what you just spent the last few weeks doing. The only thing is, we have to break it down multiple times. So I have two voltage sources here. We're going to need to solve this one twice. So let me show you how we do this. The very first step, and it's really important, is to put labels where your nodes are. So before I even do that, let's just get one thing out of the way. Remember, all of our grounds are attached. And so it's just like I had a wire going all the way here. Right? So if it helps you to draw that, go ahead and draw it. We know that's all the same spot. Now what we need to do is we need to label our nodes. And basically what a node is it's anywhere the voltage might be different. So as an example, I know that I have a node right here. I'm going to call it A, because the voltage from here to here, I actually already know it, right? We know it's 10 volts, but we're going to label it anyway. I have another node here, because I know it was 10 volts here, but I don't know what it is on the other side of the resistor. Because we have a resistor between there, it could be different. I have another node here. Again, I already know this one is 5 volts, but we're going to label it anyway. And if I really wanted to label every node, this bottom, right? All down here would be another node. And so we have 4 places where we might have to have different voltages. Now, when we solve these problems, we're going to see all we care about are the voltages at those spots. Your book does it a little bit differently. Honestly, it's confusing. I don't know why they do it that way. When we solve these problems with more than one source, we're only looking for the voltages at those nodes. By the way, should have said this up front, this is called superposition. That's what this is called. Superposition. Now, what we want to do, because this is linear, we essentially want to solve this circuit and pretend like only one voltage is there at any given time. And so let me do this. In this case, we have 2 voltage supplies, so we're going to need 2 cases. Let me show you how I draw case 1. So we got case 1 here. And for case 1, I'm only going to consider that voltage supply. And so I'm going to redraw my circuit. We will have 10 volts. I have a 100 ohm resistor. It's really important that I keep those node names. So I'm going to put A there so I don't forget that's A. Over here, I have a 100 ohm resistor. I have a 100 ohm resistor here. This is node B. Let's not forget that. Now, I want to get rid of this. And so we have to think, how could I guarantee that there would be 0 voltage from here to here? I can't just do this. Because if I do that, remember that there could be a voltage difference here. The only way we can guarantee 0 voltage is by short-circuiting it. Short-circuiting it. Trouble saying that word. Boom. Now I know, because there's no device here, there can't be any voltage difference between here and here. And so this is how we have to solve this. This is C, and we still have D here. And again, I'm going to put a ground just so it's obvious that the bottom is still ground. That's it. Now all we have to do is solve this circuit here. And remember, we don't really care about the currents anywhere yet. all I need to know, as soon as I know the voltage at A, the voltage at B, and the voltage at C and D, I'm done with this case. And so at this point, we break it down just like we always did. So I can see that we have two in parallel here, right? Notice that this here has the same top as this. They're both connected with nothing between, and they have the same bottom. So everything from this part out is solving it just like we did the last couple lectures. So I'm going to solve this by redrawing it. So we have 10 volts. I have 100 ohms. And I'm going to collapse those two in parallel just like we've been doing. And so let me bring up my calculator. So I have 100 ohms, 1 over x, plus 100 ohms, 1 over x, equals 1 over x. And so we get 50. And so here I have 50. And then again, we can break this down one more time. Nobody still told me how to stop that keyboard. I'm still waiting. 10 volts. And we have those two in series. So I have 100 plus 50, which gives me 150. And hopefully this is all familiar since you just took a test on this. Alright, we can't break this down anymore. And so now we need to solve for whatever we can solve for. And so I have got voltage and I've got resistance, so I can solve for the current here. Now remember, current isn't our goal, but we might need to solve for it in these intermediary steps. So again, remember, if we solve for current, that's V divided by R. So I'm going to pull up my calculator. And not count forward, just count. I have 10 volts divided by 150, which gives me, looks like 66.7 milliamps. I need this to do engineering mode. A lot of your calculators do engineering mode. Windows does not. And so remember, that current is the same current that's going here. So just like before, got everything done, check it off, move back. So I've got 66.7 milliamps here. Now, we know the current, we know the resistance, we can solve for the voltage drop from here to here, and from here to here. So again, I've got 66.7 e to the, what is it, negative 3? Negative 3 times 100. That gives me 6.67. Got 6.67 volts here. Again, we know what this is going to be, right? It's got to add up to 10, so it's going to be 3.3. We can do it just to make sure we got everything right. So 50 times 6.67 e to the negative 3. And we get 3 point... Wait a minute, what did I do wrong? Did you guys catch it? I did something wrong. What was it? See, we immediately know that this has to be wrong, because if I add this plus this, we only get 7 volts. Remember, it had to be 10. So let me do that again. We've got 50. Did you guys see what I did? I saw what I did. 66.7, not 6.7. E to the negative 3. And we get 3.33, 3.34 really. 3.34 volts. There's a dot there. Alright, nothing else we can solve. Bring it back. That means I now know that I've got, remember I don't really care about current, I'm just going to write the voltages. So I've got 6.67 here, and I've got 3.334 here. And now remember, all I need to do is solve for my voltages at A, B, and C. So I'm going to write it up here so we can keep track. So VA in case 1 is, remember if this is ground and we go up by 10, this must be 10 volts. VB in case 1 is if this is at 10 volts and we go down by 6.67, that must be 3.33. We can also see it here, right? If I'm at 0 and I go up by 3.34, I'm at 3.34 here. So we can write 3.33, 3.34, whatever you like. VC of 1, well look, C is attached directly to ground. And so it must be at 0 volts. And the same with VD. It's also at VD. Doesn't sound great, but it's also at 0 volts. I did not just make that joke. Alright, so we're done with case 1, and again, notice, it's the same thing we've been doing. It's not that much harder. Now we need to do case 2. So again, for case 2, we want to work with only this voltage supply. So I'm going to do that. We've got case 2. And so remember, this here, we need to replace with just a piece of wire. We short-circuited it out. We have 100 ohms here. We have 100 ohms here. Oh, the other advantage is, I promise, the next lecture is super short. It's a really easy lecture. I put a really easy one after this one. Alright, and then we've got 5 volts for that supply. So again, we're just pretending like the other ones aren't there. That's all we're doing. And so I have 5 volts here. Again, now this is what's key. This is where some people make a mistake. We have to keep our label nodes the same. Meaning, you might think to put A here, because that's where we're starting. No. A has to be in the same spot, B has to be in the same spot, C and D all have to be in the same spot. Now we just break this side down. So notice, again, this is not in series with anything because there's a choice here. And so instead we have, this has the same top here, same top here, and they have the same bottom. It's all connected with nothing else. So those two must be in parallel. So I'll combine those two in parallel. If we have 100 and 100 in parallel, remember we got 50. I have 100 here. And I have my 5 volts. Again, we have these two in series now. Now don't think these will always be the same. Notice how they both look the same when we broke it down? That's only because we had all the same value for resistors. We'll try some in a minute where they're not the same. Just keep that in mind. And so we have 5 volts here. Again, all we did was combine these two in series. Alright. We've broken it down as far as we can break it. Can't break it anymore. Let's go ahead and solve it. So we have, in this case, you know I open a new calculator every time I do this? By the time I'm done with these lectures, I have like 50 calculators open. I should use Alt-Tab instead, but I paid for the memory, I'm going to use it. Alright, so what am I doing? I'm talking so much, I'm doing it backwards. We got 5 volts divided by 150 to get the current. And we get 33.3 milliamps. So now we have 33.3 milliamps going this way. Bring that back, check it off, don't forget the check mark. Bring it off back to here. 33.3 milliamps going that way. Now we know the current, we need to calculate the voltage drops. Oh God, what did I just do? No, don't go away resistor. There we go. Alright, so we've got 33.3 milliamps times 100. Bring up the calculator. I did Alt-Tab that time. 33.3 e to the negative 3 times 100 gives me a voltage drop of 3.33. So we have a 3.33 volt drop here. Across this, we've got the same thing times 50. 33.3 e to the negative. Why is there no negative on the keyboard? I use my mouse every time. Times 50. Boom! 1.67. 1.67. Bring that information back to here. And so I now know that from here to here, that's this drop. We have 1.67. Again, that's also the same as the drop here, because remember those were in parallel. 0.67. And from here to here, we have 3.33. Alright, I think we can get ABC now. So in this case, notice our A voltage is tied directly to our ground. And so in case 2, so VA2, we have 0 volts for A. For VB2, well, if it's 0 here, and we go up by 167 from here to here, you can see from negative to positive, that must be 1.67 volts. So I have 1.67 volts at VB2. VC2, go away, I need more space. VC2 we have, well, it's 0 here, and it goes up by 5 to get to here. So VC2 must be 5. What's going on? So we have 5 volts here. VD2 is still at ground, so it's 0 volts. And now we've solved it for every case. Last step, people, last step. All we need to do to get what the actual value at A was, so the actual value here, is add up. Always add. This is why it's easier in the book. The book uses currents, and you gotta sometimes subtract and sometimes add. None of that. Always add up the voltages. So I've got 10 volts plus 0 volts gives me VA's actual voltage was 10 volts. So that's VA. VB, we've got 3.33 plus 1.67. So that's going to be 5 volts. So VB is 5 volts. Just adding it up. For VC, we have 0 volts plus 5 volts. So that's going to give me a VC of 5 volts. For VD, we have 0 volts plus 0 volts, so that's 0 volts. Now we know the voltage everywhere in the circuit. I can solve for anything. So I think your book asks you, what's the current going this way? Well, remember, to get the current, we just need to know the voltage drop divided by the resistor. If it's 5 on this side, and it's 0 on this side, that means there must be a 5 volt drop across that resistor. And so the current going that way is just 5 divided by 100. 5 divided by 100. And so we get 0.05, which is 50 milliamps. And so notice, we can solve for anything. If I wanted to know the current going this way, it's just 10 minus 5. So we get a 5 volt drop between the two and divide it by 100. And that's it. So I think it's simpler to solve it this way. Let's do another example. Alright, you ready for another one? Oh, what is this? We were just starting to understand it and I had to go and mess it up again. What is this thing? What's this over here? We haven't worked any problems with that before. Is that what you're thinking? Come on, you were kind of thinking that, right? What if I told you that's a current source? We've seen them before. We haven't really worked with them, but we've seen them before. Good news is, these things make it easier. If you see a current source, you'd be like, thank you, Dr. Poe, for making this problem much easier than it would have otherwise been. The idea behind a current source is it already gives you the current. We know now that the current going in this direction is 100 milliamps. That's what the arrow means. And like I said, the good news is it actually makes solving these problems easier most of the time. So let's see how we do it. We still have two sources. I got one here, and I got one here. So we're going to have to use that funny superposition stuff. We have two cases because we have two sources. So we've got case 1, and I already made a mistake. Remember, most important rule, we have to label our nodes. We can also do this to make it easier. So again, just picture there being a wire there because all grounds are connected. And we've got a node here. Because again, the voltage could be different anywhere there's a piece of wire. We have a node here between these things, so I'm going to call this B. We have a node here, we'll call that C. And I've got a node down here that I'll call D. Alright, so now we just need to redraw the circuit with only one source. So we'll keep the voltage source first. So I've got 10 volts, 220. 100, 220, and then we have our current supply. So remember, for the voltage, we just short-circuited. And the reason is that the only way I can guarantee there's the same voltage here as here is by drawing a wire. Remember, if there's a wire, there can't be a voltage difference between here and here. I can't do that for a current source, right? We have to guarantee there's zero current. If I just put a wire here, there will definitely be a current here. The way we guarantee there's no current is by opening the circuit. And now we can be sure no current can flow this way. I will relabel my nodes just so we don't forget where they are. A, B, C, and D. And now we just break it down like we always do. This is a problem that's similar to your book, but I made it trickier just so we know how to do this. Notice, when I break this down, you might be thinking this one is in parallel with this one, but it's not. Because that circuit is open, no current can flow this way. Remember, you have to have a complete circuit for current to flow. The only way the current can flow is that way. Because current can't go this way because it's an open circuit. Imagine if this was water and you had a pipe going this way, but you closed that pipe. Water can no longer flow in that direction. And so, believe it or not, when we break this down, we only have two resistors, a 220 and a 100 in series. That's it, nothing else. It's one of the reasons current supplies make these easier to solve. So if I break this down, I've got 10 volts. That looks like a 16, doesn't it? 10. Oh, that's even worse. What am I doing? We got 10 volts, and we have a 220 and a 100 in series and nothing else. So if I add up 220 plus 100, that gives me 320. Can't break this down anymore, so we're going to go ahead and start solving. Remember, I is equal to V over R, and so that's going to give me 10 volts divided by 300. What did I do? I already messed it up. You know, I shouldn't tell you this. This is the second time I've solved this problem. I recorded the whole video, and I realized I made a mistake on like step 1, kind of like I'm doing now. 10 divided by 320. So we get what? Looks like 31.2 milliamps? No, 31.3 milliamps. Let's round correctly, right? Move that over 3 times. 31.3 milliamps. So I have 31.3 milliamps going in this direction. Check it off. Nothing else we can do here. Bring it back to here. So we have 31.3 milliamps going in that direction. So we'll calculate our voltage drops. From here to here, we have 31.3 e to the negative 3 times 220. That gives me 6.89, we'll say. 6.89 volts. So 6.89 volts there. And then we have that same 31.3 milliamps flowing this way. Remember, all of it has to go this way. It cannot go this way because it's an open circuit. And so I've got 31.3 e to the negative 3 times 100, which gives me 3.13 volt drop that way. So I've got 3.13 volts this way. What would be my drop from here to here? What's really important that we know this, remember, I is equal to 0 because there can't be current going that direction. V is equal to I times R, and so if I is equal to 0, that means the voltage is also equal to 0. So there's a 0 volt drop from there to there. Again, if there's no current, we can't have a voltage drop there. And so now we can get our values. VA in the first case, well, this is ground, and from here to here, it goes up by 10 volts. So that's 10 volts. Notice, again, even though we have a current supply, all we're looking for are the voltages. VB of 1, well, if it's 10 volts here, and we drop by 6.89, that leaves what? 3.11? Looks like 3.11. Again, we could look at it this way. It's 0 here, and it goes up by 3.13 here. And so that also gives us something really close to that. So keep it simple. We'll say 3.13. VC of 1. Okay, now this is a really, really tricky part, so pay attention here. At VB, we said it was 3.13 volts. It drops by 0. So if I do 3.13 minus 0, it's going to be 3.13 here too. Tricky. 3.13 volts. And then finally, our VD is equal to 0 volts. That's it. Wow. It's not it. I'm lying. That's half of it. We got to do case 2. So let's try case 2. So for case 2, we're going to keep the current source and get rid of the voltage source. Remember, to get rid of a voltage source, we always short circuit it. Then we have 220. We've got 100. we've got 220. And we have our current supply, which was 10 milliamps? No, 100 milliamps. 100 milliamps. Alright, now we need to break it down. Now notice the 220 does matter now, so we got to be careful. Again, we've got these share the same bottom, and they share the same top, and so we have those two in parallel. And so we've got 220 in parallel with 100, and then we have a 220 over here. So we finish drawing it, and then we'll calculate it. So we got 100 milliamps here. We have 220 in parallel with a 100. So that's 220, 1 over x plus 100. This feels familiar. 1 over x equals 1 over x. 68.8, we'll say. So we have 68.8 as our resistor value. You know what? Let me write it on the other side because that's where I write. Ah, no, I'm messing it all up. 68.8. Alright, now we could break this down one more step, but notice we don't really have to. Like, I could add the 200 to the 68.8, but we already know the current, and we have them in series. So again, the current supply is going to make it easier here. I can actually just start from this step. I have 100 milliamps times 220. Notice that the drop always begins on the side the current enters, so that's why we put the plus on the right side. We have 100 milliamps times 220. So we have a 22 volt drop there. So right here we have a 22 volt drop. And then we have another drop here. And again, the plus is on the top because the current is entering from this direction. And so I've got 100 milliamps times 68.8. And that gives me a 6.88 volt drop there. So we have a 6.88 volt drop here. So again, we're done with all we need here. So bring it back from here to here. We have a 22 volt drop. Across these two in parallel, we have a 68.8. I wrote it diagonally because it's both across this and across this. It's the same. I forgot to label my nodes. You didn't remind me. If you were in class, I'd yell at you. A, B, C. Again, remembering we have to keep the same locations for A, B, and C. Now we can see that A is attached directly to ground. So in the second case, VA of 2 is equal to 0 volts. VB of 2, well, if it's 0 volts here and it goes up by 68.8 across that, it must be 68.8 at V2. So we have 68.8 at VC of 2. Well, it was 68. What am I saying? 68. No, I almost messed this up again. I'm going to have to film it for a third time. It wasn't 68, guys. It was 6.8. Remember? 6.8. So VB from here to here was 6.88. That's what we calculated here. I don't know what's wrong with me today. 6.88. Okay. VC of 2. If it's 6.88 here, and we go up by 22, that means it must be 6.88 plus 22, or 28.88 there. So on C2, we have 28.88. And VD of 2, again, D is still attached to the ground, and so it's 0. So we have 0 volts here. So now we know our final values, or we can solve for them, right? VA is 10 plus 0, so it is 10 volts here. VB is 3.13 plus 6.88. So that's going to give me almost 10, almost exactly 10, but pretty close. We got 3.13 plus 6.88. That gives me pretty much exactly 10 volts. And then finally we have VC, which is 31.33 plus 28.88. We got 3.13 plus 28.88. 32.01. I'm just going to say 32. That's too close. So we have 32 volts here. And VD is 0 plus 0, so we have 0 volts here. Now again, notice we know all the voltages, so we can solve for anything. I think the book wanted to know what I2 was. Well, to get I2, we need to know what the voltage difference is across this resistor divided by that resistance. And so notice on the way you get the voltage difference is we take one side, so one side is 10 volts, and we subtract the voltage on the other side. In this case, it's 0 on the other side, and we divide it by 100. So to get the difference across the resistor, take one side and subtract the other side. If I do that, we've got 10 divided by 100. And so we get 0.1, which is the same as 100 milliamps. That's it for this problem. Not too bad, right? Let's try one more. I'm going to give you the hardest problem from the homework and from the book, so I think it's actually one of your homework problems. So you want to pay attention to the next one. Let's do it. Okay guys, so I'm going to be honest with you. This is actually the second time I've recorded this part of the lecture. Originally I had to solve a problem, and it turned out to be way more difficult than I had intended. It's not that I don't think you can solve it. I just think that it's probably something that's more difficult than I would ever give you on an exam, and I don't want to freak anybody out. So what I'm going to do is I'm still going to upload me solving that problem. I'll do it as an extra video if you want to watch it, and you should watch it because you can solve things like this. It was very similar to the problem I'm going to solve now, but it had a few of these things upside down. It had an extra resistor that sort of made things way harder than they would normally be. And so I'm going to solve this one instead. Still, check that other one out, but this is sort of more like you might see on an exam or something like that. So remember, with step 1, whenever we're solving superposition, we have to label our nodes. And so we just do that anywhere that there might be a different voltage. So I'm going to say it could be different here. We can see that it's 40, but I like to put them there anyway. Again, we have a resistor between there and here. We have another one here, and here, and finally there's one more here. So sometimes it's good to start with, where are we going to need to know the voltages? Well, I'm going to have to know the voltage when I'm done at VA, VB, VC, VD, VE. The other thing we can see is that we have 3 different sources. I have 2 different voltage sources, and I have a current source. So my whole goal in solving this problem is to know what is VA1, what is VA2, what am I saying VA2? What is VA1, what is VB1, what is VC1, what is VD1, and what is VE1. And remember, because this has 3 sources, we're actually going to have 3 cases. So I'm also going to need to know what is VA2, VB2, VC2, VD2, and VE2. And then finally, by the time we're done, we're also going to have a VA3, VB3, VC3, VD3, and a VE3. So that's really all we're going to need to solve these problems. That's all we're going to need. That's a lot, right? But you get the idea. So let's go ahead and try to break this down. So for case 1, I'm just going to work left to right so I don't forget anything. It's pretty easy. So for case 1, we're going to work with that first voltage supply. And so I'll draw it right away. We've got 40 volts. We have a 1K resistor. Now remember, this is a current supply, so how do I make sure it's gone? There can be 0 current across that branch. We have to open it. Boom, it's no longer there. Makes the problem a lot easier. Alright, then I got 8.2K. Then again, we have another supply here, that's 60 volt. Remember, I got to get rid of it. I have to make sure there's 0 voltage across that. I can't open it because you can have a voltage across an open. We got to short it, right? Now, if I put a piece of wire there, there can't be a voltage difference across a wire. And so we no longer have to worry about it. I then have a resistor that's 560. and I've got 1.5K. Remember, the next thing I want to do is I want to label my nodes, because as soon as I know the voltages of those nodes, we can quit this. I don't want to waste any time. As soon as I'm done getting those voltages, we're out of here. And so I need to know the voltages at those places. Now, let's start to break this down. And it looks like a big circuit, but it's actually way easier than it looks. You know what? I made a mistake. Should have called me out. If you were in class, I'd want to hear about it. I forgot to label our grounds, right? Let's make that the ground. You can put it anywhere you want, but this is the bottom of all the supplies, so I think it makes sense. Alright, now if we look at this, right, I need to break this down. It looks like I have this in series with this, right, because let's trace our current. Current starts here, comes along this path. It can't go down because it's an open circuit, so it has to come this way. When I get at this point, what happens? Now, you might think the next two, this is in parallel. It's really not. Right? The current is never going to go this way. Not going to happen. Right? It's always going to make a right turn here and go back. Why do you think that is? Well, notice, we got a free path here. Current takes the path of least resistance. It's not going to choose to go through a resistor when it's trying to get to here. Right? This would be like, picture being on a street, right? The street's got two lanes. In one lane, you have a traffic jam. You get a bunch of resistance. The other way, sweet open road. Nothing at all in front of you. You're not going to choose to go in the lane that has the traffic jam. And so just like that, current's going to go only this way. What that means is in this problem, these two resistors, only in case A, but in case A, those two resistors are like they're not even there. And so when I break this down, notice I've only got a 1K and an 8.2 in series. That's all that's there. And so when I redraw this, I'm going to note that. We have a 40 volt. We have two resistors in series. I'm going to collapse them together. And that means I have a 9.2K resistance. And again, the reason is, notice that the current comes up, goes through the 1K, then has to go through the 8.2, and then it's back to the ground that it wants to get to. And so 1 plus 8.2K is 9.2K. So notice, even though this looks like a big scary problem, it's sort of the easiest case we've broken down so far. So then I gotta, what don't I know? I don't know my current. So I gotta solve for the current here. Bring up our trusty calculator. I've got 40 divided by 9.2 e to the 3. And so we get, what is that? 4.35 milliamps. So we've got 4.35 milliamps. Check it off because we're done. Bring it back. And that means going this way, I have 4.3 milliamps. Now what don't we know? We don't know the voltage drops. So I need to solve for the drop from here to here. And I need to solve for the drop from here to here. Notice we've got everything else. In fact, let's already go ahead and fill in what we know. So I know, what do I know? I don't know much. No, I do know stuff. I know that at VA, this is 0. So if we go up by 40, VA must be at 40 volts. I know already that VE, because it's at ground, as it's 0 volts. But notice, if it's 0 volts here and there's just wire, it's also 0 volts here. So I know VC as it's 0 volts. Well, if it's 0 volts here and there's no current going this way, that means there's a 0 volt drop across that. And so it must be 0 volts here too. So we already know VD before we really even started. So that means all I got to figure out is what is the value of VB. It's the only thing we're missing. So I've got 4.3 milliamps times 1K, right? We've got our current going this way times the 1K. And if I do that, we've got 4.35 e to the negative 3 times 1 e to the 3. So that gives me just a 4.35 volt drop. So we've got right here a 4.35 volt drop. So if it is 40 volts, we know right here it's 40, right? So if it's 40 volts and I go down by 4.35, what's that mean it must be at B? 40 minus 4.35 gives us that it's 35 point, let's just say 35.7. Let's round that. You okay with that? I'm okay with that. 35.7. And so we've got 35.7 volts for VB1. We're done with case 1. I don't ever want to see it again. You'll get to see it again because you got to watch the video. Alright, case 2. So in case 2, remember we're going to work with that current supply. Current supplies don't scare you, right? They better not. Make it easier. Alright, so we've got, remember we're going to make this a short circuit now, because we got to get rid of that. I'm using the right one. There we go. So we got to get rid of that. That's not the same color. I switched, didn't I? Alright, so we get rid of that. We've got our 1K. Now we've got our current supply. And what was that? That was 0.5 amps. Then we've got 8.2K. Again, remember this voltage supply that's here, we have to just short it out. We've got our 560. And we've got our 1.5K. Alright, so let's get and label our nodes. We've got A, we've got B, we've got C, we've got D, we've got E, and we've got our ground. And so just like I did before, let's see, what do we already know the voltages of? Well, I know E is 0. C is attached straight to the ground here, so it must be 0 volts here. D again has got 0 on both sides, so it's 0 here. A is attached straight to ground, so A is 0. So again, the only thing we don't know is B. Now before we solve this, let's see how's the current going to flow. Well, we know we have 0.5 amps starting here, right? It's going to go up and it has a choice. So some of the current's going to go this way, some of the current's going to go this way. The current that goes to the left is going to come back around and boom, it's back to ground. So it's going to go like that. What about the one that goes this way? Again, it's going to come this way. And again, it's not going to go this way. That's not going to happen, right? It's not going to go through a resistor when it has a straight wire straight to ground. And so that's all of our current. And so if you notice, what do we have when we break this one down? Again, these two aren't even in the circuit. All we have is a 1K and an 8.2K in parallel. Because as the current comes up, it has to go left through a 1K or right through an 8.2. Before I break it down, let me just redraw that and show you what I mean. Remember, because it's here in the middle, that might confuse you, you can always redraw it. And so if I trace my finger, it comes up and it has two choices. If it goes down the left side, it runs into a 1K and then it's back to ground. If it goes through the right side, it has to go through an 8.2K and then it's back to ground. And so if it scared you having it in the middle, remember, you can always redraw it so it's on the left if that makes you more comfortable. And I think this is a simpler circuit to look at. And so now we can see we've just got those two in parallel, so I'm going to redraw that like that. And notice that all we needed was B, right? We know every voltage but B. As soon as we figure out B, we're done. Let's not lose our numbers then. We know B is right here, right? Because notice it was the spot that was right on top of the current supply. So as soon as I figure that voltage out, I'm quitting this case. Alright, so if I collapse those two, we've got 0.5 amps. This comes up, comes over, and we have those two in parallel. And this, remember, is B. Pull up my calculator. I have 1 e to the 3, 1 over x, plus 8.2 e to the 3, 1 over x, equals 1 over x, and we get 891. So I have 891 ohms. And so what can we figure out now? Well, I can figure out the voltage drop. Remember, this is ground. I can figure out the voltage drop across that resistor. So I'll pull up my calculator. Remember, voltage is equal to current times resistance. And so I have 0.5 times 891, and I get 445.5 volts. Go away, Discord. No, I'm busy. 445.5. But notice, if this is 0, and this goes up by 445, that means B must be 445.5 volts. Again, remember, when we're doing these cases, all we care about are those voltages. So I'm done with this case. Let's fill out everything we know. I know that VB is 445.5 volts. So we got 445.5 volts. I know, remember, we said the rest of them. VA is at 0 because it's attached to ground. VB we just figured out. VC is at 0 because it's attached to ground. VE is at 0 because it's attached to ground. If I have 0 current going this way, and we know that V is equal to I times R, and so if I is 0, that means the voltage drop from here to here is 0. So if it's 0 here and we go down by 0, it must be 0 here. And so we know everywhere else in this case is 0 volts. 0, 0, 0, 0. That's it. See, this problem looks so horrible and it's breaking down really easy. Let's do case 3. So for case 3, this is probably the longest case. Remember, we've got no voltage supply here because it has to be removed. We've got 1K here. We have no current supply because we got to remove it. So we open it. We've got 8.2K here. We have a supply here. And that supply was how much? 60 volts. So we got 60 volts here. We have 560. And we have 1.5K. Again, we want to label our nodes, making sure we keep them in the same spot. So we got A, B, C, D, and E. Again, right away, we know some of these, not quite so many. We know that, what do we know? We know A is at 0, because it's attached straight to our ground here. We know E is at 0, because it's the ground. We technically know C's got to be 60, because if it's 0 here, and we go up by 60, from here to here, it's got to be 60. So really all we're looking at is for B and D. Man, my Discord is blowing up today. That class has an exam today, that's why it's going so crazy. I'll answer them in a second. Or you know what? Can we mute this? Let me see if I can mute this thing. I can quit. There we go. Alright, so moving on. So again, this one's got the supply in the center, which I know a lot of students don't like. So don't let it freak you out. We can redraw it if we want to. We don't actually have to redraw it, but we can redraw it if you want to, right? So if I redraw it, let me draw the 60 here. We start with 60. All right. What I would do if I were you is I would trace it with my finger. It's hard because I can't draw two things on the screen at once. But we come up and we have a choice to make. So I'm going to indicate that on my circuit. I come up and I have a choice. So I can go down one path or I can go down the other path. If I go down, let's say the left path, I have to run into an 8.2. After that, I have to run into a 1K. And then I'm back, right? So let me show you what I'm doing. We took the left path. I had to go through an 8.2. I had to go through a 1. And then I was back to the bottom of the supply again. And so let me do that over here. I go through the bottom and then I'm back to the supply. If I take the right path, so in other words, if I go this way, I have to go through a 560. And then I have to go through a 1.5K. And then I'm back again to the bottom of the power supply. And so like I said, if this makes it easier, by all means, do it this way. The only thing I'll recommend you do is go ahead and label your nodes right away so you don't forget where it is, because this kind of looks different than this. So again, remember the top of our power supply, so right here, this is C. So that's C now. From C, if I go across to the other side of the 8.2K, that's B. So at this point, B is here. If I keep going, down here is A. On the other side of the 1K, it's also E. Alright, if I go the right path, on the other side of the 560 is D. So that's here. And then again, we're back down to E and A and all that stuff. So again, if you redraw, just make sure you keep track of where the nodes are, because it gets a little bit confusing. So the circuit gets easier, but labeling the nodes gets a little bit more confusing. Alright, if we collapse this now, we can see that we've got two in series, and those are in parallel. So remember, we can only do series or parallel. We can't do both at the same time. We can't do the parallel because they're not in perfect parallel until we get rid of the series. So let's do the series first. So I've got 60 volts, and I'm going to collapse those two in series. If I have 8.2K and 1K, that's going to give me 9.2K. And then finally, I've got on the right side, I hate the keyboard, I've got 1.5K and 560. So that's going to give me 2.06K. There we go. 2.06K. Alright, now we can collapse these two in parallel. And so I've got 60 volts. So we've got, what was it? 9.2K. 9.2 e to the 3. 1 over x. Plus 2.06K e to the 3 1 over x equals 1 over x. So what do we get? 1,683. So let's say 1.68K. Round a little bit there. 1.68K. 1.68K. Alright, now we gotta figure out what can we figure out. So remember, we can solve for current, which is voltage divided by resistance. And so I've got 60 divided by 1.68 E3. That gives us what? 35.7 milliamps? Yep, 35.7 milliamps. Bring that back. Nothing else we can figure out here. So I know that the total current here is 35.7 milliamps. I want to point something out. Breaking this down to this step was kind of unnecessary. I did it just because we normally do it, but notice these two are in parallel and I knew the voltage across both of them. I could have immediately solved for this current, and this didn't help me at all. So if you notice that, good on you. You don't have to break it all the way down every time. Basically, when we have a voltage supply and we have them all in parallel, we already have everything we need to solve for it. Knowing the total current here didn't really help me with this circuit very much. So, like I said, I did it because we normally do it, but didn't have to. So now remember, we can solve for these currents because we know the current is voltage divided by resistance. I know both the voltage for this resistor and the current and the resistance. We know we've got 60 volts divided by 9.2 e to the 3. That's going to give me 6.52 milliamps. So we've got 6.52 milliamps. And then on the right side, I've got 60 volts divided by 2.06 e to the 3. And that's going to give me 29.1 milliamps. 29.1 milliamps. The good thing about knowing this is it kind of checks our work, right? Both of these look good because they add up to what we know had to be the total, that 35. And so let's bring our information back. We're done with everything we can solve for here. So I know that the current going down this path is 6.52 milliamps. I know the current going down the other side. Remember, extra credit if you can tell me how to get rid of that keyboard from popping out. 29.1 milliamps. And so all we need to solve for are the voltages. So I've got a voltage drop here, and a voltage drop here, and I've got one from here to here, and I've got one from here to here. And so let's just do it. We've got 6.52 e to the negative 3 times 8.2 e to the 3. And so I get a 53 point, let's do 53.5, that sound good to you? 53.5 volt drop across the first one. Do the same thing for the second one, 6.52 e to the negative 3 times 1k. So I get a 6.52 across the second one. Alright, other side. We've got 29.1 e to the negative 3 times 560. I get 16.3 milliamps. Volts. 16.3 volts. And we've got on the other side 1.5. Okay, so we got 29.1 e to the negative 3 times 1.5 e to the 3. And I get 43.7, we'll call it. 43.7. Again, both of these look good because they add up to 60. So 6.52 plus 53.5 adds right up to 60. Again, we rounded a bit. 6.3 plus 43.7 also adds up to 60. Everything looks good. Now remember, all we need are the voltages. So let's start filling them out. I know that A is 0 and E is 0 because they're at ground. I know that D, if this is at 0, D must be 43.7 volts because it goes up by 43.7 volts. I know that C is 60 because if it's 0 here and it goes up by 60, it must be 60 there. I know that A is 0, we said already, and B must be 6.52. Notice technically we didn't even need to solve these. We were able to get all our voltages. And so in the beginning of this class, I was saying solve for everything, figure everything out. Now we can start to be a little bit smarter about it. We only really need to solve for the things that we need to know. And we already know everything. I don't even need to go back to this step. And again, that's because I wrote my nodes here. So let's fill this out. VA is at 0. So in VA3, we have 0 volts. VB, right, it's 0 here, goes up by 6.52, must be 6.52 volts there. So 6.52 volts there. VC, well, if it's 0 here and it goes up by 60, it's got to be 60 here. So we have 60 volts here. VD of 3, well, if it's 0 here and it goes up by 43.7, VD is at 43.7. So we've got 43.7 volts here. And VE, well, remember VE's down here. It's attached to the ground. And so it's got to be 0 volts. And that's it for case 3. So let's fill out our final results. We have VA is 40 plus 0 plus 0. So it's at 40 volts. VB is, I can't do that in my head. Let's add that up. So for VB, we have 35.7 plus 445.5 plus 6.52. So we get 487.7. 487.7. VC, we've got 60 plus 0 plus 0, so it's at 60 volts. VD, we've got 43.7 plus 0 plus 0, so it's at 43.7 volts. And we've got VE, which is at 0 plus 0 plus 0, is at 0 volts. So now we know every voltage in the circuit. We could solve for anything that I asked you. Like, let me give you an example. Let's say I wanted to know, I'll give you the most complicated one I could give you. I want to know what is the current going, let's say, through the resistor RL. What's the current going that way? Well, notice, what do we know? I know that the voltage at this point is 43.7. I know the voltage here, because it's ground, is 0. So the voltage across that 1.5 is 43.7 volts. Remember, to get the voltage difference, we have to subtract the voltage on one side, so 43.7 volts, minus the voltage on the other side, which is 0, and divide that by the resistance, which is 1.5K. And so if we do that, we have 43.7 minus 0, which is 43.7, divided by 1.5 e to the 3, and we get 29.1 milliamps. So notice, we've got everything I could possibly ask you. Anything I can possibly ask you, you can get. So again, like I said, your book does this a little bit differently, and in my opinion, way more complicated. So I think this is an easy way to do it. I want to tell you, if you made it this far, you're doing absolutely great. This is probably, without a doubt, the hardest, longest, most painful lecture of the entire DC course. So congratulations for making it this far. If you have questions, you know how to reach me. Talk to you again soon. Next lecture, way easier. Super short, way easier. Congratulate yourself.